Have you ever wondered what makes your smartphone so smart? Or how your laptop can play incredible games and stream movies without even breaking a sweat? You might think it's just the battery or the screen, but the real magic is happening deep inside, on a scale so small, it would blow your mind. The hero of this story is a tiny, unsung champion called the MOSFET. It's a component so fundamental and so numerous that there are more of them on Earth than there are grains of sand on all the world's beaches combined. Yes, you read that right. These little guys are the secret superpower behind almost every single piece of modern technology you use every single day. Think about your morning. Your alarm clock that wakes you up, packed with MOSFETs. The coffee machine that brews your perfect cup? You guessed it, MOSFETs are in there, controlling the heat and timing. When you get in your car, the engine control unit, the infotainment system, and even the electric windows are all orchestrated by millions of these microscopic switches. They are the invisible workhorses that have quietly powered our leap into the digital age. Without them, the world as we know it would grind to a halt. Our phones would be bricks, our computers would be silent boxes, and our world would be a lot less connected and a lot less fun. So, why should you care about some microscopic thing with a weird name? Because understanding the MOSFET is like getting a backstage pass to the greatest show on Earth, modern technology. It's about pulling back the curtain and seeing the fundamental building block that makes everything possible. Learning about this isn't just for engineers in lab coats. It's for anyone who has ever felt a sense of wonder about how things work. It's for the curious minds who want to know the why behind the what. This knowledge connects you to the very pulse of the 21st century, giving you a new appreciation for the incredible ingenuity packed into the devices you hold in your hand. In this journey, we are going to dive deep into the world of the MOSFET. We're going to break it down in a way that is super simple, super clear, and most importantly, super interesting. Forget complicated diagrams and boring textbooks. We're going to think of it like a tiny, ultra-fast light switch. We will explore how this simple idea became the most manufactured object in human history, and how it enables the complex dance of ones and zeros that defines our digital reality. So, get ready to have your mind blown, because you're about to understand the secret that powers your entire world. Let's do this. Alright, let's get down to it. What in the world is a MOSFET? The name sounds super technical: metal oxide semiconductor field effect transistor. Whoa, that's a mouthful. But forget all that. At its core, a MOSFET is just a really tiny switch. Imagine a light switch on your wall. You flip it up, the light turns on. You flip it down, the light turns off. A MOSFET does the exact same thing, but instead of using your finger to flip it, it uses a tiny bit of electricity. And it can turn on and off billions of times per second. That incredible speed is what makes your computer's processor so fast and powerful. Let's break down its job. A MOSFET has three main connections, which we can call the source, where the electricity comes from, the drain, where the electricity wants to go, and the gate, the magical switch. Normally, electricity cannot flow from the source to the drain because there's a barrier in the way. But when you apply a small voltage, a tiny electrical signal, to the gate, something amazing happens. It creates an electric field that opens up a channel, like lowering a drawbridge, allowing electricity to flood from the source to the drain. Remove that tiny voltage from the gate, and the bridge goes back up, stopping the flow. On, off, 1, 0. That's the language of computers, all controlled by this simple action. Think of it like a garden hose. The source is the spigot, the drain is the nozzle, and the hose itself is pinched shut in the middle. The gate is your hand. When you don't squeeze the hose, no voltage on the gate, no water can get through. But when you apply pressure with your hand, apply voltage to the gate, you unpinch the hose and water flows freely. The best part is, it takes very little effort from your hand to control a huge gush of water. In the same way, it takes a tiny amount of power at the gate to control a much larger flow of electricity between the source and the drain. This is called amplification, and it's another one of the MOSFET's superpowers. This on-off switching ability is the bedrock of all digital logic. By combining millions or even billions of these tiny switches in clever patterns, engineers can create logic gates that perform simple calculations like AND, OR, and NOT. These logic gates are then combined to build more complex circuits that can add numbers, store memories, and execute the instructions that make up your favorite app or video game. Every pixel on your screen, every note of music from your headphones, and every letter you type is the result of billions of these MOSFETs flipping on and off in a perfectly choreographed, lightning-fast ballet. It's not magic, it's brilliant engineering. Before our hero, the MOSFET, took over the world, there were other components trying to do the same job. One of the old-timers was the vacuum tube. If you've ever seen a picture of an old-school computer from the 1950s, you've seen vacuum tubes. They were big glass bulbs that looked like light bulbs, and they got incredibly hot. They could act as switches and amplifiers, but they were huge, fragile, and burned out all the time. A computer built with vacuum tubes could fill an entire room and needed a massive air conditioning system just to keep from melting. The MOSFET, on the other hand, is microscopic, uses very little power, and generates far less heat, allowing us to shrink a room-sized computer into something that fits in our pocket. Another key player is the bipolar junction transistor, or BJT. The BJT was a huge step up from the vacuum tube and helped kickstart the transistor revolution. It was smaller, more reliable, and much more efficient. For a long time, it was the king of the hill. However, the BJT has a fundamental difference. It's controlled by current, not voltage. Think back to our garden hose analogy. To turn on a BJT, you have to run a little bit of water through a separate, smaller hose to control the main flow. A MOSFET, being voltage controlled, is like just using your hand. You don't waste any water or current to activate it. This makes MOSFETs way more power efficient, which is critical for battery-powered devices like your phone or smartwatch. This efficiency is the MOSFET's killer feature. Because the gate is electrically isolated, almost no current is needed to keep it in the on or off state. It just needs that initial voltage push. This is why we can pack billions of them onto a single chip without it instantly melting or draining your battery in 5 seconds. BJTs, on the other hand, constantly draw a small amount of current to stay on, which adds up when you have millions of them. For high-power applications, BJTs still have their place. But for the digital logic that runs our world, the low-power nature of the MOSFET is unbeatable. It's the undisputed champion of efficiency. So, while we have to give credit to the pioneers like vacuum tubes and BJTs for paving the way, the MOSFET is in a league of its own. It's the perfect combination of small size, incredible speed, and amazing power efficiency. This trifecta is what allowed for the explosion of personal computing and mobile devices. It's not that the other components are bad. It's just that the MOSFET is uniquely suited for the job of creating dense, complex, and low-power integrated circuits. It was the right technology at the right time, and it completely changed the game for electronics forever. So how do you actually build something so small that you could fit millions of them on the head of a pin? The process is one of the most precise and incredible manufacturing feats in human history, and it all starts with sand. Well, almost. It starts with silicon, which is purified from sand. This silicon is melted down and grown into a massive, perfectly structured crystal called an ingot. The ingot is then sliced into ultra-thin, perfectly flat discs called wafers. These shiny gray wafers are the sterile canvases upon which billions of MOSFETs will be painted, layer by layer. The process happens in a place called a clean room, which is thousands of times cleaner than a hospital operating room. Even a single speck of dust can ruin hundreds of MOSFETs, so workers wear full-body bunny suits to prevent contamination. The first major step is called photolithography. The wafer is coated with a light-sensitive material called photoresist. Then, a pattern of the circuit, like a stencil, is projected onto the wafer using ultraviolet light. The light hardens the photoresist in specific areas. When the wafer is washed, the unhardened parts wash away, leaving a perfect stencil of where the next layer should go. This is how they define the incredibly tiny areas for the source, drain, and gate. Next comes a series of steps that build up the MOSFET. One key process is called doping. This is where they intentionally introduce tiny amounts of impurities, like boron or phosphorus, into the silicon to change its electrical properties in very specific regions. This is done using a machine called an ion implanter, which literally shoots atoms into the wafer like a subatomic machine gun. Then, they grow an incredibly thin layer of silicon dioxide, which is essentially glass, on top of the silicon. This insulating layer is what isolates the gate, and its thinness is critical to the MOSFET's performance. Finally, they deposit a layer of metal, or polysilicon, to form the gate itself and the connections that link all the MOSFETs together. This entire sequence of layering, patterning, doping, and depositing is repeated dozens of times to build up the complex, multi-layered structure of a modern chip. It's like building a skyscraper, but on a microscopic scale, with each floor representing a different layer of circuitry. After all the layers are complete, the wafer, which now contains hundreds of identical chips, is tested. Tiny robotic probes touch down on each chip to make sure it works perfectly. Then, a diamond saw dices the wafer into individual chips, which are then packaged in the little black plastic rectangles you see on a circuit board. And just like that, you have billions of tiny superheroes ready to power your next device. Now that we know how these incredible devices are made, let's talk about why quality is so unbelievably important. Imagine you have a chip in your phone with 5 billion MOSFETs. What happens if just one of them doesn't work right? What if it gets stuck in the on position or refuses to turn on at all? That single faulty switch could cause your favorite app to crash, your camera to freeze, or in a worst-case scenario, your entire phone to stop working. The reliability of the entire system depends on the perfection of every single one of its billions of parts. It's a mind-boggling challenge of consistency and precision. This is why the manufacturing process is so ridiculously controlled. The clean rooms, the bunny suits, the robotic precision. It's all to ensure that every single MOSFET on every single chip is a perfect clone of the one next to it. A tiny variation in the thickness of the oxide layer, a misplaced atom during the doping process, or a microscopic scratch on the wafer's surface can lead to a defect. These defects might not cause the chip to fail immediately. Instead, they can be like tiny ticking time bombs, causing the device to fail months or years down the line. You want your car's engine, computer, or a medical device to work flawlessly for its entire lifespan, and that reliability starts here. Think about the extreme conditions some electronics face. The chips in your car have to work perfectly, whether it's a freezing winter morning or a scorching summer afternoon. The electronics in a satellite have to endure the harsh radiation of space for decades without a single hiccup. This robustness is engineered right into the MOSFETs themselves. During development, chips are put through intense stress tests. They are baked in ovens, frozen in freezers, zapped with electricity, and run for thousands of hours to find any potential weaknesses. The data from these tests is used to refine the manufacturing process to build stronger, more resilient MOSFETs. Ultimately, quality control is the unsung hero that makes our modern world possible. It's the guarantee that the complex symphony of billions of switches will play out perfectly every time you turn on a device. When you buy a product from a trusted brand, you are not just paying for the name. You are paying for the immense investment in quality control and testing that ensures the MOSFETs inside are of the highest grade. So the next time your computer boots up flawlessly or your GPS navigates you without a glitch, take a moment to appreciate the invisible, relentless pursuit of perfection that made it all possible. We've been on an awesome journey today, from the sand on the beach to the billions of tiny superheroes powering the device you're using right now. We learned that the mighty MOSFET is basically a super fast, super small, and super efficient light switch. We saw how its voltage-controlled design and low power usage made it the undisputed champion of the digital age, leaving older tech like vacuum tubes in the dust. And we got a peek inside the incredible ultra-clean factories where these microscopic marvels are born, layer by painstaking layer. It's truly one of the coolest engineering stories of all time. The most amazing part of all this, you understood it. If you followed along, your brain just processed and stored information about one of the most important technologies ever invented. That's because your brain is the most powerful supercomputer on the planet, and learning new things is its favorite thing to do. Understanding how the world works isn't just for smart people. It's for curious people. It's for you. The more you learn about science and engineering, the more you realize that the world isn't magic. It's just a series of really cool puzzles. And the best part is, you have the ability to understand how those puzzles are solved. My goal is always to show you that science and engineering are fun, accessible, and incredibly empowering. Knowing what a MOSFET is gives you a new level of appreciation for the technology you use every day. It connects you to the brilliant people and the incredible effort that goes into creating the modern world. This is just the beginning. There are so many more amazing topics to explore, from the physics of rockets to the biology of your own body. The adventure of learning never has to stop, and I want to be your guide on that adventure. So, if you enjoyed this little dive into the microscopic world of electronics and you want to keep feeding your awesome brain with more cool science and engineering content, you know what to do. Help support the mission of making learning fun by hitting that like button. Share this with a friend who you think would find it interesting, spread the knowledge, and most importantly, make sure you subscribe and turn on notifications so you don't miss the next adventure. Thank you for spending your time with me today. Stay curious, and I'll see you in the next one.